This is the third lecture of the 5-lecture series on polarization. In this last lecture, which was the second one, we studied Malus law, which defines the intensity of the transmitted beam when a plane polarized light passes through a polarizer. This intensity is proportional to the square of the cos of the angle between the direction of vibration in the incident light and the path direction of the analyzer. We also considered superposition of two electromagnetic waves under different conditions, that is, the waves having electric field in the same direction or electric field in perpendicular directions and with varying phase difference between them. In the present lecture, which is the third one in the series, we shall consider phenomena of double refraction. We shall look at dichroism and study the working of a nickel prism. Let us start with the double refraction. Now, the superposition of two plane polarized waves under different conditions, as described earlier in the last lecture, can be experimentally studied and analyzed by using the phenomena of double refraction in crystals of calcite and quartz. In general, all crystals except those belonging to the cubic system are anisotropic to a greater or lesser degree. Anisotropy means different properties in different directions, that is, the properties vary with the direction. Calcite and quartz are very common examples of anisotropic crystals. Chemically, calcite is calcium carbonate CaCO3, while quartz is the pure silica, silicon dioxide. Both of these show simple type of anisotropy, which characterizes uniaxial crystals. In these crystals, there is a single direction called the optic axis, which is an axis of symmetry with respect to both the crystal form and the arrangement of atoms. If any property, such as for example heat conductivity, is measured for different directions in such a crystal, it is found to be the same along any line perpendicular to the optic axis, which is the symmetry axis. It changes with angles reaching a maximum or minimum along the optic axis. Now, both of these crystals, the calcite and quartz, are transparent to visible as well as ultraviolet light. That is why they are of interest to us in this study. When a beam of ordinary unpolarized light is incident on a calcite or quartz crystal, there are, in addition to the reflected beam, two refracted beams. Remember, two refracted beams in place of the usual single one, for example, which is observed for example in glass or any other isotropic material. This phenomena is called double refraction or birefringence. The beam which travels undeviated for normal incidence is known as the ordinary ray, usually abbreviated as the O ray, and obeys Snell's law of reflection. Snell's laws are that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant, does not depend on the angle of incidence, it also does not depend on the direction of propagation. and the incident ray, the refracted ray and normal to the surface, they are all in the same plane. On the other hand, the second beam, the second refracted beam, which in general does not obey Snell's laws, is known as the extraordinary ray, is usually abbreviated as the E ray. See here, the incident beam is getting splitted into two. One is called the ordinary, the other is called the extraordinary. If the two opposite phases of this crystal are parallel, as shown in the figure, the two refracted rays emerge parallel to the incident beam and therefore parallel to each other. Inside the crystal, however, the ordinary ray is always found to be in the plane of incidence, as happens in any isotopic material. That is the normal situation, which is very common. However, this is true for the extraordinary ray only for some special directions. In general, this is not true for the extraordinary ray. If the incident light is normal to the surface of the crystal, the extraordinary ray will be refracted at some angle that is not 0. You note this is a very special feature. If the incident beam is normal, the extraordinary ray will be reflected at some angle that is not 0 and will come out parallel to but displaced from the incident beam. The ordinary ray will pass through straight, undeviated, which is usually the case, which really should be the case, because the angle of incidence is 0, the angle of refraction cannot be anything but 0. Now, if we put a polarizer behind the calcite crystal and rotate the polarizer about the line n prime, then for two positions of the polarizer, when the pass axis is perpendicular to the plane of the screen, the E ray will be completely blocked and only the O ray will pass through. Because the direction of vibrations in the O ray is along the pass direction of the polarizer that is getting through. For the extraordinary ray, the direction of vibrations is perpendicular to the pass direction of the polarizer, it is getting blocked. Remember Malus law, cos of 90 degrees is 0. That is the situation in this figure. On the other hand, when the pass axis of the polarizer is in the plane of the screen along the line P P prime, then the O ray will be completely blocked and only the E ray will pass through. I mean, the situation has just interchanged. Further, if we rotate the crystal about n prime, then the E ray will also rotate about it. Actually, the tip of the extraordinary ray will describe a circle whose center will be given by the ordinary ray. Another thing to be noted, both the rays, the ordinary and the extraordinary, are plane polarized. Remember, the incident beam was unpolarized. The double refraction in uniaxial crystals disappears when the light is made to enter the crystal, so that it travels along the optic axis, which is the symmetry axis. That is, there is no separation of the ordinary and extraordinary ray in this case. This is the case when the propagation is along the optic axis. The velocity of the ordinary ray is same in all directions. This is a very usual case that does not depend on the directions. as it happens in all isotropic materials, whereas the velocity of the extraordinary ray is different in different directions. These are given by the following equations. V of R O is equal to C upon N O, this is for the ordinary ray, 1 upon V of R E, that is the inverse of the velocity for the extraordinary ray, is given by sin square theta divided by C by N E square plus cos square theta divided by C of N O square, this for the extraordinary ray. Here N O and N E are the refractive indices of the crystal for the ordinary and for the extraordinary ray respectively, and theta is the angle that the ray makes with the optic axis. We have assumed the optic axis to be parallel to the z axis here. The C by N O and C by N E are the velocities of the extraordinary ray when it propagates parallel and perpendicular to the optic axis. Parallel to the optic axis means theta equal to 0, perpendicular to the optic axis means theta equal to pi by 2. Let us consider the equation of an ellipse in the zx plane, z square upon a square plus x square upon b square equal to 1, where a and b are proportional to the velocities of the ordinary and the extraordinary rays C upon N O and C upon N E respectively. In polar coordinates rho theta, z and x are given by z is equal to rho cos theta and x is equal to rho sin theta, and the equation of the ellipse which given above can then be written in the form 1 upon rho square is equal to cos square theta upon a square plus sin square theta upon b square. In 3 dimensions, this will represent an ellipsoid of revolution with the optic axis as the axis of revolution. Remember, optic axis is the symmetry axis. Thus, if we plot V of R E as a function of theta, we will obtain an ellipsoid of revolution because the velocity is different in different directions. On the other hand, since V of R O is independent of theta, if we plot V of R O as a function of theta, we will obtain a sphere. These are the shapes of the respective wavefronts originating from the origin. Along the optic axis, theta equal to 0 and V of R O is equal to V of R E, which is equal to C upon N O. The two wavefronts touch each other along this direction, that is the propagation being along the optic axis for the angle theta equal to 0. Let us now consider the case of VRE perpendicular to the optic axis, propagation perpendicular to the optic axis. In this case, theta equal to pi by 2. For a negative crystal like calcite, n of E is less than n of O, and therefore, V of R E for this direction theta equal to pi by 2 is equal to C of N E, which is greater than V of R O. In this case, the minor axis of the ellipsoid will be along the optic axis and the ellipsoid of revolution will be outside the sphere. On the other hand, for a positive crystal like quartz, Ne is greater than No and V of Re therefore, for theta equal to pi by 2 is greater than V of Ro. The major axis will now be along the optic axis, and the ellipsoid of revolution will lie inside the sphere. These are given in these pictures. This ellipsoid of revolution and the sphere, they are known as velocity ray surfaces. For both waves, now that is important, for both waves, ordinary and extraordinary, the space and time dependence of the electric field E, electric displacement D, magnetic induction B, the magnetic field H. See, all these quantities appeared in the Maxwell's equations. So, all of these can be assumed to be of the plane wave form e raised to the power I k dot r minus omega t for a plane monochromatic wave. Here k denotes the propagation vector and represents the direction normal to the phase fronts. In general, the k vector for the O and the E waves will be different, but d dot k is 0 for both O and the E rays. This means the electric displacement d is always perpendicular to the k vector, and for this reason the direction of d is chosen as the direction of vibration. If we assume the z axis to be parallel to the optic axis, then d dot z will be equal to 0 for the O wave. On top of this, d dot k is 0 anyway. Thus, for the ordinary wave, the d vector, that is the direction of vibration, is at right angles to the optic axis as well as to k. This means the direction of vibrations for the ordinary ray, it is at right angles to the plane containing the optic axis and the vector k. For the E wave, on the other hand, the electric displacement vector d lies in the plane containing k and the optic axis, along with the condition that d dot k is 0. Let us consider the general propagation in a doubly refracting crystal. Let us consider incident wave incident normally on a uniaxial crystal like calcite. Without loss of generality, we can always choose the optic axis to lie in the plane of the screen as shown in the figure. Two orientations of the optic axis are shown. A, B and C, D are the incident rays. B D line is the line of intersection of the incident wave front and the plane of the screen. Once the light enters the material, we find that there is a splitting. The points B and D are touched at the same time. Remember, the beam is incident normally. Now, in order to determine the ordinary ray, we draw a sphere with point B as center and radius c upon NO. Remember, c upon NO is the speed of the ordinary ray. Similarly, we draw another sphere of the same radius, because both these spheres are originating at the same instant. The points B and D become active at the same time. So, that is why the radius is same. So, for the sphere is starting from the point D. These two spheres represent the wavelets is starting from the points B and D respectively after some time. The common tangent plane to these spheres is shown as OO prime, which represents the wave front at that time corresponding to the ordinary refracted ray. Note that the dots show the direction of vibrations, the direction of the electric displacement vector E, which are perpendicular to K and to the optic axis as pointed out earlier. Remember, we are talking about the ordinary ray. In order to determine the extraordinary ray, we draw an ellipse centered at the point B with its minor axis equal to C upon NO along the optic axis, and with the major axis equal to C upon NE perpendicular to the optic axis. The ellipsoid of revolution is obtained by rotating the ellipse about the optic axis, which is the symmetry axis. Similarly, we draw another ellipsoid of revolution from the point D, identical in shape, identical in size. Remember, the points B and D become active at the same time. The common tangent plane to these ellipsoids, which will be perpendicular to K, is shown as E prime in the figure. This is the wave front corresponding to the extraordinary ray. If we join the point B to the point of contact O, then corresponding to the incident ray AB, the direction of the ordinary ray in the crystal will be along BO. Similarly, if we join the point B to the point of contact E between the ellipsoid of revolution and the tangent plane E prime, then the corresponding to the incident ray AB, the direction of the extraordinary ray will be along BE. Note that the direction of K is same here for both O and E waves. Both are along BO. Now, however, if we have a narrow beam of light incident as AB, the ordinary ray will propagate along BO, while the extraordinary ray will propagate in a different direction BE. The distance between them will go on increasing. Now, obviously, if we have a different direction of the optic axis as shown in the lower part of the figure, then although the direction of the ordinary ray will remain the same as it should, remember the ordinary wave satisfies the Snell's laws of refraction. The extraordinary ray will propagate in a different direction now. This is because the direction of optic axis has changed, and it have changed the orientation of the ellipsoid of revolution. Now, if a ray is incident normally on a calcite crystal, and if the crystal is rotated about the normal, then the optic axis and the extraordinary ray will also rotate about the normal on the periphery of a cone. The tip of the extraordinary ray will describe a circle. So far as the ordinary ray is concerned, it remains unchanged all the time. The refractive index n of Re corresponding to the extraordinary ray propagating along a direction making an angle theta with the optic axis is given by n of Re is equal to C upon V of Re, which is equal to the square root of NO square cos square theta plus NE square sin square theta. This means that along the optic axis theta equal to 0, n of RE is equal to NO, that is for the ordinary, and perpendicular to the optic axis theta is equal to pi by 2, n of RE is equal to NE. Now, as pointed out earlier, the direction of vibration for the ordinary ray is normal to the optic axis and the vector k. As such, the directions of these vibrations in this case will be normal to the plane of the screen, and that is why they have been shown as dots in the figure. For the extraordinary, they are in the same plane and they have been shown by short arrows. Direction of extraordinary ray is perpendicular to k and lies, as I pointed out earlier just now, in the plane containing the extraordinary ray and the optic axis. Thus, an incident ray will split up into two rays propagating in different directions within the crystal, and when they leave, we will obtain two plane polarized beams polarized in perpendicular directions and travelling parallel to each other and also separated from each other. We shall now consider some special cases. In the above, we have taken the optic axis to make an arbitrary angle with the normal to the surface of the crystal. We shall now consider special cases. With normal incidence again, but with the optic axis in the plane of incidence and parallel to the crystal surface, or in the plane of incidence perpendicular to the crystal surface, or perpendicular to the plane of incidence and parallel to the crystal surface. Let us consider these one by one. First, we take up optic axis in the plane of incidence and parallel to the crystal surface. The optic axis here lies along Mn. AB is the incident plane wavefront of the rays falling normally on the surface Mn of calcite. PR is the refracted wavefront for the ordinary ray, and QS for the extraordinary ray. They have been described earlier. We follow the same construction here. The wavefronts PR and QS are parallel to each other. The ordinary and extraordinary rays travel along the same direction, but with different velocities in the crystal. In calcite, the extraordinary ray travels faster than the ordinary ray. A phase difference naturally gets introduced between them as they propagate in the crystal. You see, the lower part of the figure shows the wavefronts and the direction of vibrations for the ordinary and the extraordinary beams with respect to the plane containing the beam and the optic axis. Now, let us consider the second possibility. Optic axis perpendicular to the plane of incidence and parallel to the crystal surface. AB is again incident wavefront of the rays falling normally on the calcite surface Mn. The form of the wavefronts for the ordinary and the extraordinary rays are shown in the figure. Both are spheres. the radius of the ordinary wave front is V O into T, that of the extraordinary is V E into T, where T is the time elapsed after the waves originated from the point A or B. P r is the refracted wave front for the ordinary rays, Q s is for the extraordinary. They have been obtained exactly the same way as in the earlier case. The ordinary and the extraordinary rays, they travel with different velocities along the same direction. In this case, both the ordinary and the extraordinary rays obeys the standard laws of refraction, Snell's laws. Because we find, you see, the wave fronts are spherical in this geometry. Again note, the direction of vibrations for the ordinary and the extraordinary beams given in the lower part of the figure. For the extraordinary ray, they are in the plane containing the propagation and the optic axis. For the present case, this plane is perpendicular to the screen, and therefore, vibrations for the extraordinary ray are shown as dots. In the above two cases, if the incident wave is polarized perpendicular to the optic axis, it will propagate as an ordinary wave with velocity c over n o, and there will be no extraordinary wave. On the other hand, if the incident wave is polarized and polarized parallel to the optic axis, it will propagate as an E wave with velocity c over n e, and there will be no ordinary wave. Let us now take the third case, optic axis in the plane of incidence and perpendicular to the crystal surface. The optic axis has been shown as a dashed line. A B is incident plane wave front, as in the earlier cases of the rays falling normally on the surface of the crystal M n as before. The optic axis is in the plane of incidence and perpendicular to the surface of the crystal. As I said earlier, it is shown in the figure as the dashed line. The spherical and the ellipsoidal wavelets originating from the point A touch each other at P. Similarly, those originating from the point B touch each other at R. There is no separation of the ordinary and the extraordinary rays. Both travel with the same velocity along the optic axis. Remember, which is the symmetry axis. Here the refractive index for the extraordinary ray along AQ is equal to the refractive index for the ordinary ray. The vibrations shown in the lower part of the figure are in the plane of the screen for the extraordinary ray and perpendicular to it for the ordinary ray, just following the same arrangement as in the earlier cases. Let us now consider another interesting phenomenon, the phenomena of dichroism. You see, there are certain crystals and minerals which are doubly refracting, but they have a special property, and that is they have the property of absorbing the ordinary and the extraordinary rays unequally, and in this way a plane polarized light is produced, at least in principle. The crystals having this property are called dichoric, and the phenomena is known as dichroism. Tourmaline is a dichoric crystal. This figure shows the passage of an unpolarized beam through a tourmaline crystal. It progressively absorbs the horizontal vibrations which correspond here to the ordinary ray, with the result that by the time the beam comes out, the horizontal vibrations are almost completely absorbed, while the extraordinary ray, which has vertical vibrations here, passes through without much attenuation. The tourmaline crystal is sometimes used to serve as a polarizer or as an analyzer. Now, we come to another interesting device, work as a polarizer, Nicol prism. There is another method for eliminating one of the polarized beams, ordinary or extraordinary. This is through total internal reflection and letting the other one to pass through and thus making a polarizing device. It's a very ingenious method. We know that the two beams have different ray velocities, and as such the corresponding refractive indices are different. If one can sandwich a layer of a material whose refractive index lies between the above two refractive indices, then for one of the beams the incidence will be at a rarer medium, and for the other it will be at a denser medium. This principle is used in Nicol prism, which consists of a calcite crystal cut in such a way that for the beam for which the sandwiched material is a rarer medium, the angle of incidence is greater than the critical angle. Thus, this particular beam will be eliminated by total internal reflection. This is happening here for the ordinary ray. See, the dashed outline in the figure corresponds to the natural crystal. The front face is slightly etched to change the angle from 71 degrees to 68 degrees. A layer of Canada balsam has been introduced in the diagonal plane of the crystal as shown in the figure. This material is not doubly refracting and its refractive index is 1.55, which is intermediate between the refractive index for the ordinary, which is 1.65836, and refractive index for the extraordinary is 1.48641. So, Canada balsam offers a rarer medium for the ordinary ray. The crystal is cut in such a way so that the angle of incidence at the Canada balsam layer is more than the critical angle, and the ordinary ray, which is meeting a rarer medium, Canada balsam layer, undergoes total internal reflection at the layer and is then absorbed by the sides of the crystal. The extraordinary component passes through and the beam emerging from the crystal is plane polarized. So, we have a simple polarizing device. Okay, with this we have come to the end of this lecture.